All right, recording is rolling. Welcome to Wednesday, October 18th. I got a couple of Kahoots lined up for you guys. We're going to start with inverse square law and then move on to universal gravitation. Let me find, have this ready to go here. All right, here we go. Here's universal gravitation, big theme of what we've been doing about last week or so, right? And then part of this is, see, there's an inverse square law relationship between the force of attraction and the distance, right? So 1 over r squared, right? Now, I should say a couple of these Kahoot questions you guys are about to see are actually not that relationship, but most of them are. I think there's like 10 questions and 8 of them have something to do with the inverse square relationship. A couple of them have to do with like the masses versus the force, right? Okay. And if you just look at the inverse square in isolation, here's a like a luminosity example, but similar idea, right? So like 3 times the distance, you only catch 1/9 of the light, right? And then gravity works the same way. Okay. So you guys are about to see questions about that. Here, let's go down the rest of this card here. Dual enrollment meeting in cafeteria, periods 2 and 6. Check with your 6th period teacher, see if you think this might apply to you. There's a spreadsheet going around saying what students are doing that. We finished chapter 6 and 7 puzzles yesterday in class. Well, I covered all the ones that I assigned to you guys. Let's have those 2 Friday. Probably finish them now anyway, but we had today to hold on to those because I just gave you guys your next quiz. Centripetal force, gravitation, orbits. Let's have this one due on Monday. So you guys write that in your planner. You guys got all that? All right, so with that, let's switch over and do Kahoot. So this is again inverse square law. Actually, 8 out of these 10 questions are inverse square law. Yep. Yeah. So open notes. Yeah, open notes. There you go. All right. And then here's the pin on the board. If you're about to hop in, there you go. All right. Inverse square. What if you double the distance between 2 objects? What happens to the force? I double the distance. Ooh, 3 winners. So you get a quarter of the force. All right, so I definitely need to cover that one in the notes here. So we got one mass here, different mass here. There's some, this is, we'll call R. R usually stands for radius, but if you have like a moon orbiting the Earth, that's usually why I go with that. So anyway, all right. So got this frog face looking guy. What if you double that distance? So you get these two like further away from each other. Well, the force interaction between these, the force and then the Newton's third law equal and opposite force here. So the magnitude of that force equal and opposite goes universal constant times the 2 masses multiplied together divided by the distance between them squared, right? So suppose that's like the original force, is that, right? And then we're gonna have a new force that's like double the distance. So that'd be like G_m over 2r quantity squared like that, right? Oh, but doesn't that exponent right there apply to both parts on the inside? So couldn't that be like G_m all divided by 4 times r squared, right? And then look what we have here. That's like, if I pull up this 4 in front, now I've got 1/4 of G_m over r squared. And that, this piece right here, was the original force. So it's like 1/4 of the original force. There you go. Right. So if you double the distance, the force is getting weaker, but it's like 1/4 because 1 over 2 squared. There's your inverse square law right there. You guys got that? Right. And back over here. Oh, what that flip. Right. Wait for the class one to flip. All right. All right. Who got that? Aaron, Adam, and Patrick. All right, nice. All right. Good start there. Ooh, exact opposite. What if we turn around and we cut that distance in half? Now what happens to the force? Because if you double the distance of 1/4 of the force, now we're going to do the exact opposite process. Just gotta turn right around and cut that distance in half. Now what's these? Oh, everybody got it right. All right. Yeah, it would be 4 times. Okay. All right, so that is awesome. You guys figure that out? I'm gonna real fast just go over the poster version of this, just point this out. Okay. So that one is a little trickier, but you guys got it. Right? So if you do half of the distance, right? So the force would be increasing, so it's good check to do, right? So 1/2 squared is like 1/4, but it's 1 divided by that. Guys, what's 1 divided by a quarter? 4 times, and everybody got that. All right. Man, you guys are catching on fast. All right. Sports. Double one of the masses. Okay, so this is not inverse square law. This is a different question. Universal gravity. So if you double one of the masses, what happens to the force? Yeah. So the force is proportional to each of the masses. So if you double one of the masses, then the overall force would also double, right? Right? Yeah. All right, we got Kylie, Tucker, Blakey, Adam, and Patrick on fire. How's this table? All right. What if both of the masses triple? So they triple. They each triple. What happens to the force? Triple one mass, triple the other mass, the overall force. Yeah, 9 times. Triple is 9 times the overall force. Okay. Okay, so most of you guys got the last 2 questions. I'll point them out with the poster version. Okay. So a couple questions back, it said, what if you just double the large mass in isolation, but everything else is the same? If throw a factor of 2 on this guy, the overall force would just double what it used to be. Okay. And then the question you guys just answered is like, what if you triple that and also triple that at the same time? So I got a factor of 3 and a factor of 3. Factor of 3, that's like 9 times the overall force. Right? 3 by 3 is 9. Oh yeah. I got Aaron, Kylie, Tucker, Blakey, Patrick. Oh. What if you quadruple the distance? What happens to the force? Quadruple the distance. You're real far away from each other. We guys out. What is 1 over 4 squared? Look at you guys. 1/16, right? Okay, so 4 times the separation distance. Gravity force definitely getting weaker. So it's got to be either the red or the blue, right? It can't be the yellow or green, right? Further away is weaker gravity force, right? And inverse square relationship. So 1 over 4 squared, that's like 1/16 of the original force. All right, got Andres Blake hopping in. Yeah, Tucker, Blakey, and Patrick. Exact opposite. Now we're gonna cut that distance to 1/4 of what it used to be. Closer together. 1/4. Yeah. All right. There you guys go. We got that. Yeah. So it'd be the exact opposite. All right. I was gonna, I was gonna write this out, but since everybody got it, I'll just point it out real fast on the poster version. Right? So get closer together. The force getting stronger. I got 1/4 of the distance. 1/4 squared is 1/16, but it's 1 divided by a 16th, which is like 16 times. 1 divided by 1/16 is 16 times, right? It's like a fraction and a fraction. Right? So you just flip the fraction. Yeah, 16 times the force. All right, it's doing good. Ooh, all right. What's got a third of the original distance? 1/3 of the distance. Happens to the force. Yeah, 9 times the force, right? Really similar premise to the question before it. Right? So here, I'll just navigate with this poster version again. Right? So we're cutting the distance into a third of what it used to be. So we got a third factor on this r. What's 1/3 squared? That's 1/9. But that's the denominator of this larger fraction. So 1 divided by 1/9, that's 9 times the force. Right? Get 9 times the force. Okay. Hey, what do you think would happen if you do the exact opposite process? What if you started off with some distance and you effectively triple that distance? Right? Let's do it right here. What is 3 squared? Right? And then 1 over that. So it'd be getting weaker by that much. I think that might be the next Kahoot question. Oh, I meant to mention too. We're halfway through. Oh no, here. Let's see. All right, we got Adam, Matt, Blakey, Patrick on fire. Look at that. Triple the distance. What happens to the force? Right there. That's what some of my first posters used to look like. I got really pretty posters. Oh, look at you guys. Yeah, 1/9 of the force. Because 1/3 squared. There's inverse square law right there. Inverse square law. All right. Patrick's still in the lead. And 2 left. Suppose you weigh 500. Suppose you weigh 500 newtons. Now you're going to a planet that has the same mass but half of Earth's radius. So we like crunch down the planet. Same mass, half Earth's radius. I'll help you guys navigate this. So it's kind of like you effectively get like half the distance to an object. Right? Suppose you choose like a point mass, some r away versus half that distance away, right? If you throw in 1/2 r here and you square that, because what's 1/2 squared? It's like a quarter. But what's 1 divided by a quarter? It's like 4 times. You think you'd be 4 times as heavy on this little tiny planet? I think you'd be 4 times as heavy. But what's 4 times 500? 2,000, right? 2,000 newtons, right? Okay. Right. So here, I do want to write that one out. This one, I know from last class, useful to have these notes. So I got R versus half R. Okay. I should have a side note. Say, guys, if these planets were the same density, what should the mass of this planet be compared to this one? It should be less, right? Right? How much less? This is kind of a tricky question because do you guys remember this from way back in the day? Right? So if you scale up something by some factor, different properties change, but according to what dimension they're in, right? So anything linear, anything to do with areas, anything to do with like mass or volume, right? Mass occupies volume, right? Okay. So maybe instead of a factor of 3, maybe it's a factor of a half, right? Right. So okay, because volume-wise, what is 1/2 to the power of 3? What's half times a half times a half? Is that an eighth? Right, an eighth, right? Right. Half of half is like an eighth of something. Right? This planet down here should have an eighth of the volume of this guy, and if it was made out of the same material, it would also have an eighth of the mass, right? But we didn't do that. We're going to do a simplification. We're going to say it's supposed to say mass, right? That was just a whole side thought. So don't worry about that for the good question. Right? How much would you weigh on the little tiny guy versus on the large planet? Right? Well, you would actually weigh more on the small one, right? Because remember, it's the same mass, but you're effectively like closer to the planet that way. Right? So your weight would be like universal constant times the mass of the planet times your mass divided by some general distance squared. Right? And this bottom one, we throw in a factor of a half squared. So maybe this is the force on the large planet. The force on the small planet, say your weight, Gmm over 1/2 r squared. So this is what okay. 1/2 squared is like a quarter. And then 1 divided by a quarter, that's like 4 times. Right. Now, if this whole GMM on R squared was originally 500 newtons. That's right here. There's 500 newtons. So now the small planet or weight, your weight on the small planet would be 4 times 500 newtons. There's where you get 2,000 newtons. Now you weigh 2,000 newtons. Oh yeah. Oh, okay. Yeah. I think you're thinking. Yeah. Let's go back here. Okay. You're actually kind of right about that. We can find some notes from last class. Where is this? Here it is. Okay. You guys remember? Here, guys, everybody look up here. Everybody look up here. Okay. Do you guys remember a few days back I took you guys journey to the center of the Earth? I think this is what you're thinking of, right? So if you actually tunnel down inside a planet, then everything above you in elevation turns into like a series of eggshells that cancel out, right? So it's like if I got a guy standing like halfway down to the center, like right about there, right? Everything above him in elevation cancels out. So it's as if he's standing on a small planet that's just beneath him, right? And actually, yeah, his weight would be less. It'd be going down until it gets to 0 right at the center, right? The difference between that from the other day and what we just did is that we're saying that the mass of these two planets, is actually the same, right? So you like crunch this down, like, right? So if it starts off like a giant puff planet, you like crunch it down to like it's made out of lead, so it's like so incredibly dense, right? Over here, we were saying uniform density, so you're like subtract everything out from here, and actually it wouldn't be mass m anymore; it'd be like an eighth of the mass, right? Over here, we're saying like we're going to crunch this down, so it's two different scenarios, right? Okay. All right. I'll say it one more time because that's a little bit tricky. Right? So the other day, like about a week ago or so, when we were going over this, right, we're saying if you tunnel down inside of the planet, everything above you in elevation cancels out like a series of eggshells. So the only effective mass pulling on you is what's beneath you in elevation, which would not be the full mass. It might be like, in this case, like an eighth of the original mass, a little tiny mass. Okay? So your weight goes down. Right? But if you have some planet and you crunch it down, you're effectively getting closer to the center, but it's the same mass that's pulling you. It's just at a closer distance. So you actually would feel heavier. Yeah. So it's yeah. Yeah, that's a fun one. That's a fun one. All right. Let's see how you guys did here. Is it here? All right, got a few winners. I got Matt, Blake, Adam, Blakey, and Patrick in there. All right, for the win, for the win. All right, suppose you weigh 900 newtons on Earth. Now we're going to a planet with the same mass, but 3 times the Earth's radius. Ooh, just puffed out, giant puff planet. Here, I'll help you guys navigate this one too. So gravity field's the same. The mass of the planet's actually the same if you compare the two masses. Okay. Your mass is the same, that didn't change, right? But it's kind of like sitting on a crazy tall tower where you're effectively further from the center of the planet. Each of these planets we're going to treat as kind of like a point mass at its own center mass, right? So we're tripling that R. This one is a factor of 3 squared. It'd be 9, right? And since that's in the denominator, it's like 1 over that. So should on the right side, you have a 1/9 of the weight that you do compared to the left, right? So now you weigh less and less and less. What's 1/9 of the original 900 newtons? 100 newtons, right? There you go. There you go. All right, kind of the reverse scenario of the one right before it. Okay. Those last 2 questions, the opposite things. All right, to the podium with the bronze, Adam. With the silver, Blake. And the gold. Oh, Patrick. And runners up, Blakey and Matt. Right, nice job there. All right, I gotta queue up the next. Start that. Let's do some little switching here. I'm gonna pause this video while I'm getting the next one going. All right, recording's resumed. We got questions on gravitation coming up here. Gravitation. Thanks for hopping on that one pretty quick. All right. Gravitation questions. Newton hypothesized that the moon There you go, all the above. Okay, it's attracted to Earth, has a tangential speed, keeping it from falling into the Earth, it's falling around the Earth. Okay, yeah, there you go. It's about orbital speed. All true. All right, points on the board. And Kylie in first. If the mass of the Earth increased with no change in radius, so we're just making the Earth more massive, what would happen to your weight? Yeah, your weight would also go up. Ooh, okay. Yeah, let me flip my screen real fast. Okay. Maybe that was a short time one. Okay. Okay. So all we're saying here is we're just gonna make more Earth more massive. Instead of being a regular Earth, maybe we see another planet, it's like the same size, but then we land on it, it's made out of lead. Oh boy. So this big M just increased. And all these other variables stay the same. So your weight would also increase. Okay? Your weight would increase directly proportional to that mass increase, wouldn't it? Mass tripled, your weight would also triple. All right. I got Andres, Adam, Blake, Patrick, Kylie. If the radius of Earth decreased with no change in mass, ooh. All right. It's actually did pretty good on that one. Yeah, your weight would go up. Okay. I want to remind you guys that we did actually see pretty much this question a few minutes ago. You guys remember if you take some planet and you crunch it down to a little tiny planet? It's the same mass, right? Same mass. Right? One way to think of this is like you're effectively closer to the center, right? And then how these numbers play out, if it has half the radial size, you have 4 times your weight. Okay? So the guy on the small planet actually weighs more than the guy on the large planet. Yeah, in like the real universe, right? The difference would be like the mass would probably also scale up something proportional. Like this, the large planet should have 8 times the mass of the small planet in this case, right? But if that's not the case, if they're the same mass, then you actually would weigh more on the smaller radial size one. Yeah, right. If it's for equal masses, that would be true. Yeah. I'll check a scenario there. All right, we got Andres, Blake, Adam, Kylie, Patrick. The gravitational force between 2 massive spheres. It's always an attraction, depends on how massive the spheres are, depends inversely on the square of the distances between them. Or I should say is proportional to that. Yeah, there you go. There you go. All the above. Other kinds of force like electrostatic force can be either attractive or repulsive, but gravity, we're just going to take that to be attractive. All right, and Kylie, back to the top spot. 2 objects move toward each other. As they get closer, the gravitational force between them does what? Yeah, increases, right? Like if 2 objects are crazy far away from each other, gravity feels really weak. Like the gravity force between like Earth and Mars is like almost nothing. It's like negligible, right? But Earth and the Moon, ooh, that's enough to hold the Moon in orbit, right? And then like you and the Earth, you're on the surface. Okay. So the closer you get, the more the gravity force. The further away, the less gravity force. All right, Patrick, back to the top spot. Suppose gravitational force between 2 massive spheres is 100 newtons. Now we're going to double the distance between the 2. Now what's the new force? A couple asteroids floating around in space. 100 newtons. Then maybe they like kind of drift away from each other. Oh, yeah. So it'd be a quarter of the original amount. A quarter of 100. The issue is 25. That'd be newtons. Right. So we're saying what if it got a couple asteroids and they kind of float past each other and they got like double the distance now. Right? So factor 2 on that r, double the distance. Well, 2 squared is 4, so it's like 1/4 of the original amount. 1/4 of 100 is 25 newtons. 25 newtons. Oh, and here's what I meant to mention. that take-home quiz I gave you guys do see the first few questions are some of these straight off this Kahoot. So FYI, there you go. All right, we got Andres, Kylie, Adam, Blake, Patrick, fire. The force of gravity is greatest on you when you are standing where? Yeah, right on Earth's surface. Right. Where'd you guys see that? You guys remember this from last week? This from last week, right? So if you're on the surface, well, here's a graph that, in terms of gravity field, as a function of radial distance from the center. Here's some general radial distance from center. There's a very special fixed radius, capital R, also on the graph, right? So what's the gravity field in terms of that? Now the question said weight, but if you just take your mass multiplied by gravity field, you get your weight, right? So right on the surface, you weigh the most. If you tunnel down into the earth, you weigh less until you get to the very center, it goes to zero. That's a direct relationship there. I think I proved that to you guys the other day without that be a direct relationship. If you stand on a really tall tower, right, then your weight would be less because you're further away from the earth. Right? You take off in a rocket, further away you get, it's gonna asymptotically approach zero. Right? Right, that's that one. I think that slide I just showed you guys is gonna become a new poster too. I haven't printed out quite yet. All right, Matt, Blake, Kylie, Adam, and Patrick. A lunar month is about 28 days. If the moon were closer to Earth than it is now, then what would a lunar month be? Oh, yeah, okay, nice. Less than 20 days. All right, so let's do a few examples of satellites. Now, you guys remember, here, actually, I should flip my screen and remind you guys of something here. Right. You guys remember for satellite motion, here's orbital speed, maybe for like a circular type orbit. Notice the mass of the satellite itself canceled out along the way, right? So orbital speed has nothing to do with mass of the satellite, right? I can think of a couple, let's do a couple satellites orbiting Earth. How about International Space Station? Does anybody know? Low Earth orbit. Low Earth orbit. How long does it take International Space Station to go around the Earth? About 90 minutes. Yeah, right. I think we may have run the numbers the other day, got like 85 minutes or something, or well, my class, I think I did that, right? How about now the moon is like 28 days. The moon's like way out there. Now, those are different masses themselves, but that has nothing to do with this, right? Canceled out, cancel out the moon, the International Space Station, right? Right. Okay, so the closer you are to like low Earth orbit, closer it is to 90 minutes. The closer it is to the moon, closer to 90 days, or sorry, 28 days, right? I think yesterday we saw the geosynchronous orbit. There was like a 24-hour rotation, right? So that would be somewhere in the middle, right? Right, there you go. This also maybe you could bring in Kepler's third law, right? Kepler's third law is kind of related to that too. Right, the time period versus the distance. It's like a square cube relationship. All right, Patrick's still in the lead. If you're 400 newtons and stand on top of a tall tower, so you're 1 Earth radius above Earth's surface. Now, how much do you weigh? Well, it's not. Yeah, right. Oh, nice, nice. Yeah, so you guys have got a quarter of the weight. A quarter of 400 is 100. So point this out. Capacity here. Because I got a picture of this. Okay? So if here's the Earth radius, and if you're on top of a tower, also that distance tall. Right? Now, of course, there's nothing on Earth that's even close to that, but just make believe, right? You would have effectively doubled your distance from the center of the Earth, right? So if you follow inverse square law, double the distance, you got a quarter of the weight. Right? Or on this graph, those graphs from the gravity field, but it's the same shape, right? It's force gravity, right? If you go from R to 2R, right, double your distance, right? If I do this exactly right, I got kind of close, right? You should have like a quarter of your original gravity field, so a quarter of the weight. I'm on fire. Patrick in top spot. Oh, my screen just freeze. Okay. Let's pause this operation right here. All right, recording resumed, and we are back. Oh, let's flip my screen. This is here. There we go. Okay. So gravitational force between two spheres, let's say two asteroids floating around is 100 newtons. Now we're gonna cut the distance in half. So maybe these asteroids are drifting towards each other. You do 1 divided by a half squared, which is 1 divided by a quarter, which is 4 times the force. 4 times 100 is 400 newtons. 400 newtons. There you go. All right, we are back rolling. According to Newton's laws, a rock and a pebble will fall with the same acceleration in a gravitational field because yeah, ratio of force to mass is the same. Right now, the forces are the same because the weights are, the forces are different because the weights are different. Right? Did I play you guys a video that involved there was like Paul Hewitt talking about like two kids on an island, like which one's getting to the ground first for the Hershey's bar? Yeah. Yeah. Okay. Yeah. Yeah. That's this. This is the question that goes along with that story. Right. So one kid said, "Well, I think the heavier one because it's got more force." Right. In isolation, that's actually true, except they do the experiment. It doesn't. They hit the ground at the same time. Another kid, another part of the island says, "Well, I think the smaller one first because it has less mass, which is less inertia, so that should make it accelerate faster." Which again, in isolation would be okay. Then you do the experiment and they hit the ground at the same time. If you put the two kids' ideas together, right? So more force, but also more inertia, right? It's a wash. Right? So same acceleration. Same acceleration. Okay. All right, Matt moving up, Patrick in the lead. The value of acceleration due to gravity. Yeah, all the above. Here, point this out on the poster real fast. You guys see a poster above that closet door? All right, here you go. Here's gravitational field, and those were all answer choices. The big G, the big M, and the radius of the planet. Those are all factors into the gravitational field of the surface of the planet. Okay. GM on R squared. All right, Matt moving up. Patrick still in the lead. Gravitational field strength at the center of the Earth. All right, look at you guys go. So 0. All right, real fast. You guys were thinking of this right here, right? The center. Right, so there's the graph version. If you're hanging out in the center, every single grain of sand on Earth is pulling you a different direction. It all cancels out. You're floating around like an astronaut. Yeah, 0 gravity field. When a star collapses to form a black hole, what happens to its mass? By the way, our sun is not large enough to form a black hole. You can do a star about 3 times the size of our sun. The end of its life, it's fusion runs out, it would collapse to tiny point. Yeah, okay. But did you guys learn something called conservation of mass? Maybe in chemistry class, conservation of mass. You can't create mass, you can't destroy mass. When a star collapses down to form a black hole, its mass doesn't change, right? Our star, by the way, is thinking of becoming a neutron star, not actually a black hole, but right. All right. All right. Yeah, conservation of mass. Mass stays the same. Okay, now that's actually a lead into this question. Suppose that happened. Earth sun collapses to a black hole. What does Earth do? Or does it? Probably freezes separately. No, orbit the or orbit it just as it does now. All right, one winner. Let's take a look here. Okay. So as you got the sun here, here's the Earth here. So S for sun, E for Earth. It's going around elliptical type orbit. It's got some tangential velocity like this. Some radial distance are going on. Right. Now, if the sun collapses down to a black hole, it had some mass before. That mass doesn't change, right? The gravitational force between the two, G M over distance squared, none of that changes, right? Nothing changes here, right? So this orbital speed is the same.
Right, you're saying right now that our sun could be a black hole because our
Yeah, well, I guess the other part of that story is we would freeze over, so it get really cold. But yeah, in terms of orbital mechanics, yeah, nothing actually changes. Who got that? Oh, Patrick got that. Right. For tidal forces to be significant, there must be tides. Yeah. So you want a proportional difference between the close and the far side. Oh, here, I'll point out this picture about that. Okay. So like the Earth and the Moon, right? There's definitely some kind of a tidal action going on. Right? The Moon is closer to one surface of Earth than the other side. Now this picture's not to scale, but you just get the idea, right? You guys see that? Right? Actually, the other answer choice that was wrong is actually the opposite of what you want. Right? It says something about a large distance between two objects, which would actually like decrease the tidal force. Right? So if the two objects are pretty close to each other, now you get a larger proportional difference between the force to the close side versus the force to the far side. You guys actually do that. Oh, most of you guys got that. Nice, almost there. All right. If the radius of Earth were half of what it is now, picture mass is okay, mass the same. What would be the value of G? Gravity field. I'll help you guys out. So you're going to crunch down the Earth. We did this one before today, right? So half the radial size, but everything else is the same. You do GM over R squared. What's 1 divided by 1/2 squared? Right? So 1/2 squared is 1/4. What's 1 divided by 1/4? Is that 4 times, right? 4 times. What is 4 times about 10 meters per second squared? There you go, right? Here. Yeah, trying to show you guys this real fast here. Right? It was this from our notes earlier. Well, just divide by your own mass to get gravity field. Right? So sorry, it's not that one. It's the same. It's this one here. It's the same idea, right? Okay, so if you crunch down there to smaller size, you get 4 times the 4 times your weight, 4 times the gravity field. We're getting close. Just enough time for these last few questions right here. A circle is a special case of. Just remember breaking out the string and the pins. Anyway. Yeah, what shape are you guys drawing with the string and the pins? Ah, ellipse, right? A circle is a special case of an ellipse. Object placed exactly halfway between Earth and the Moon. That object will fall toward the. So what's going on more? Earth or the Moon? Exactly halfway between the two. It's gonna fall towards the Earth because the Earth has more mass. And for the win, Early bird communication satellite hovers same point above Earth's equator indefinitely. Why? Ooh,
No, that's right.
this reminds me of a question we did yesterday. You look up in the sky, the satellite's always there, all day, every day. There's one way to make that happen. And she park it at a special location where its orbital period is 24 hours. One winner. Yeah. Guys, that's called geosynchronous. You guys remember geosynchronous from yesterday? Geosynchronous? With the bronze, Kylie. With the silver, Blake. And the gold, Patrick. Runner up, Adam and Matt. Okay, nice job, guys. Oh, just in time to. Man, that is a wrap on today.